Welcome to this lecture series on microwave engineering and microwave techniques. So, in this series, we will be discussing and we will be learning about the various aspects of microwave theory that are useful for us in understanding the transmission and generation of microwave signals. So, firstly, in this course, what we are going to learn, let us have a brief overview of that. Firstly, what is a microwave signal? So, microwave signal is basically an electromagnetic wave. Microwave signal is also an electromagnetic wave. So, it is an electromagnetic wave. It is a type of EM wave having a particular frequency ranging between 1 gigahertz to 1000 gigahertz. So we all of us know that the electromagnetic spectrum, right? We have the frequencies from 1 gigahertz to several thousands and lakhs of gigahertz, so 10 power 20 gigahertz, right? And this electromagnetic spectrum is actually divided into various types of signals. So on the far end, where the high frequency is very high, we call these signals as the gamma rays. And then the next we have X-ray, and then we have UV rays, right? And we have visible spectrum, a small part as a visible spectrum, and then we have infrared rays, and then we have radio waves. Okay, so based on the frequency of the signals, the electromagnetic waves are categorized or given different names. Okay, so all of them are electromagnetic waves. Only based on the frequency, right? They have been given the different names. Okay, and not only this, so as the frequency of the signal increases, right, the energy of the signal also increases. The energy of the signal also increases. So the gamma rays have highest energy, whereas the next X-rays, UV rays, and as we go on from this side, right? So the frequency here decreases. So from here, so these signals will have lesser energy, and hence they also the transmit the rate at which or the distance they can travel is also less. Okay, so this is the thing. So out of this entire spectrum, there is one range of frequencies ranging from 1 gigahertz, so somewhere in the radio waves, so 1 gigahertz to 10 power 3 gigahertz, so 10 cube gigahertz, okay, so 1000 gigahertz. So this particular signal, this particular spectrum is what we call it as the microwave spectrum. Okay, so and the waves and the electromagnetic waves of these frequencies are called as the microwaves. Okay, why you call them as microwaves? Because the wavelength of these signals will be in the range of several centimeters to meters. So wavelength, right? As we know, wavelength generally depends upon lambda is inversely or lambda is equal to c by f, or it is inversely proportional to 1 by f, isn't it? So, right, if I take 1 gigahertz, so lambda, right, 3 into 10 power 8 divided by, so 1 into 10 power 9, so which approximately gives me as 0.3, right, 0.3, so which is nothing but 0.3 meters. Okay, so right, so I will get, okay, I will get my ranges, right, the wavelength range will be ranging from a few centimeters to, right, meters. So that is why these waves are called as microwaves. Okay, so these microwaves find an exhaustive applications in various fields. For example, all our radar communications, radars, satellites, okay, missiles, okay, and satellite telephony, all our communication satellites, everything, all of these, right, medical imaging, okay, for treatment of cancer, etc., etc. So there are a huge number of applications for microwaves. That is the reason why this microwave spectrum that is there is called as the most useful part of the electromagnetic spectrum, along with the radio wave part. Okay, so this has quite a few applications, right, in both scientific, medical, and as well as communication spectrums. Okay, so therefore, a careful study of microwave signal generation is very much useful and very much required. And at the same time, so there is one more very important aspect as, so we, as we say, the microwave signals, their range or their frequency is between 1 gigahertz to 10 cube or 1000 gigahertz. So the frequency of the signal is very high. So we can consider it as to be high. Okay, so very high frequency, right? So whenever, right, as per the Planck's constant, as per the Planck's rule, so as the frequency increases, the energy carried by the signal is also very high. The energy carried by the signals is also high. So therefore, the microwave signals, right? Okay, the microwave signal energy will be very high, and hence it is difficult to handle them with the help of the conventional coaxial cables or twisted pairs. Okay, so the transmission lines that we studied. Okay, so we gave waveguides also as an example of transmission lines, isn't it? So the traditional transmission lines that we use at low frequencies, such as coaxial cables or twisted pairs, are of not much use in case of microwaves. Why? Because the energy carried by the microwave signals is large. Okay, so therefore, and for transmitting the signals, for transmitting the signals of this frequency of this microwave signals, we require special kinds of transmission line structures, such are called as waveguides. Okay, so in this subject, we will be studying both the properties of the microwave signals, okay, and also how these microwave signals can be transmitted through these guided structures, which are called as waveguides, a type of transmission line. Okay, so before going into in detail study, okay, we will be discussing about all the facts, all the concepts related to the electromagnetic spectrum, the different bands of microwaves, etc., etc., in the first unit. But before that, let us have a brief understanding of this entire subject. So what we are going to discuss in the 5 minutes. Okay, so this is actually strictly according to the OU syllabus. But the concepts that we discuss here can be related to any other general university curriculum. Okay. So in the first unit, okay, so which is about the unit one, which is about the guided waves. Okay, the guided waves, right, or also called, right, or also what we will be discussing about is a parallel plane waveguide. So this first unit will be discussing about guided waves or the study of parallel plane waveguides. Okay, yeah. So yeah, first of all, this microwaves, as I said, it is a microwave is a part of electromagnetic wave, isn't it? So there is a direct connection between a microwave signal or microwave what you study in this to the electromagnetic theory that we study. It's a basically microwave signal is just a part of is just an electromagnetic signal. So you might have studied in the EMTL, in the electromagnetic theory and transmission lines, up to a point where, for example, in the generation of waves, so you generate an electromagnetic wave with the help of Faraday's law. Okay, so we all know what is a Faraday's law, right? So whenever I have a charge, okay, moving with some acceleration, then I will get an electromagnetic wave. Okay, so how do you make the charge accelerating? You can either rotate the coil or you can apply a time varying current. Okay, so that is the concept of generating the microwave signal. Okay, so simple point. So a microwave or electromagnetic wave. Okay, let us not come to the microwave, let us stick to electromagnetic wave. Electromagnetic wave will be generated whenever, right, there is a time varying current passing through a coil. Simple. So how do you get the time varying current? You can that's what I said, accelerating charges. So whenever there are accelerating charges moving in a closed path, we will be getting electromagnetic waves. How do you produce those accelerating charges? One, you can use a time varying current, or second, what is the other alternative? You can use a coil which is rotating. Okay, so that's what we call it as the motor method and the generator method. Okay, whichever the way we can generate electromagnetic wave. This is the basic principle. Okay, and this electromagnetic wave, okay, so again we have assumed to be only present in particular directions, which we call it as uniform plane waves. So that also we discussed what is a uniform plane wave. So a electromagnetic wave in which E bar electric field is only along one axis, magnetic field is only along one direction, and the resultant wave is perpendicular to the two directions. Okay, so if the wave is propagating in a mutually perpendicular direction to both electric field and magnetic field, okay, that means E bar, H bar and the wave, if all of them are perpendicular to each other, then such a wave propagation or the wave will be propagating in only one plane. So that is what we call it as uniform plane wave. Okay, so we discussed how electromagnetic wave can be generated, what is a uniform plane wave, how does this uniform plane wave behave in different media. Like a perfect dielectric is there. If I have a perfect dielectric, then the electromagnetic wave will travel through that perfect dielectric without any losses. Whereas if I take a perfect conductor, so in case of a perfect conductor, the electromagnetic wave will not travel at all. Okay, so right, we have discussed about practical dielectric, practical conductor also. Okay, so that we discussed. Then we discussed about, right, what are the characteristics like intrinsic impedance, gamma, okay, propagation constant, attenuation constant, phase constant, etc, etc. So all that part we discussed in the EM theory, right? And then we also discussed how the EM waves, right, gets transmitted from one media to the other media. So if I'm sending a signal, electromagnetic signal from medium 1 to medium 2, okay, we have normal incidence, we have oblique incidence, right? And what is normal incidence? What is oblique incidence? How does that right affect the signals, etc, etc, everything is discussed there. Okay, right, so all these whatever we discussed in electromagnetic theory, it is related or it is intended with the free space. Okay, we have considered a medium to be unbounded, not just free space. Either you take air media or free space or water, whatever you have taken, all of that you have taken as an unbounded media. That means there are no boundaries. Okay, there are no boundary conditions or there are no boundaries for the electromagnetic wave to travel. Understood? So whatever the concepts that we studied in electromagnetic theory till now, right, whatever we have, all these are related to unbounded media. Okay, so there is, right, no boundary conditions or no boundaries for the electromagnetic wave or for the signal to propagate. Okay, now whenever, right, this unbounded media is directionless, it doesn't have a direction, it can spread all over the three dimensions, and also losses will be high. So for example, if we want to transmit this wave inside a guided structure, okay, so inside a guided structure with very less losses or very low losses, and also, right, with the perfect right directivity. Okay, so there might be certain circumstances where we want to transmit electromagnetic wave through a guided structure. Okay, through a guided structure. So such kind of thing, right? Such a thing will give us different results. That means it will affect the electromagnetic wave in a different way. That is, whenever I apply the boundary conditions or whenever I apply the guiding structures to an electromagnetic wave, right? We will be encountering a different situation. So what will happen whenever this electromagnetic wave is propagated through a guided structure, right, is what we are going to study exactly in the first unit. Okay, so the first, right, unit, the in our syllabus, we will be discussing, right, what is going to happen or what is the effect of the guiding structures or the boundaries. Earlier it was unbounded, now when I put boundaries to this wave, so what is the effect of these boundaries on the electromagnetic wave is what we are going to discuss in the first unit. Okay, so for here I take, right, a general structure, a theoretical guided structure, which is what we call it as a parallel plane waveguide. So nothing but a waveguide that is passed through, right, sorry, a waveguide that is constructed through two parallel plates. Okay, two parallel plates placed over, right, an axis like this. Okay, so this is the general guiding structure. So inside this, right, we will be taking about this, right, guiding structure, and we will be understand here it is just a theoretical assumption, right? Practically we do not have any kind of parallel plane waveguides. It is not possible practically to construct two absolutely parallel waveguides that are open boundaries, isn't it? So it is just a theoretical as a guiding structure. So using this theoretical guiding structure, which is called as a parallel plane waveguide, we will understand what is the effect of applying the boundary conditions on the electromagnetic wave. So here our idea is to understand how the electromagnetic wave characteristics change whenever I transmit it through a guided structure. Okay, so that's what we call it as guided waves. Okay, guiding here means so the wave is guided inside the two boundaries. Inside the two boundaries, it is not unbounded; it is bounded like this. So inside a boundary, how does the EM wave propagate? Okay, what are the field components? Okay, so all those things. How does the field vary? How does the electric field vary? How does the magnetic field vary? All that we will understand. Okay, so this unit basically deals with guided waves, means the electromagnetic waves which are guided with the help of boundary conditions or boundaries. Okay, right. So here we will be discussing right the first thing we'll be discussing is about the general structure of a parallel plane waveguide, as I said. So what is the general structure of the parallel plane waveguide? Okay, so we will first discuss that. Then we will be discussing about the different types of different types of polarizations of electromagnetic waves in case of in case of oblique incidence, because that is what we will do, right? Okay, so that means see here, so this is my parallel plane waveguide. Okay, now I am transmitting or I am incidenting the signal, electromagnetic wave signal, with some angle, right? So this kind of incidence is called as oblique incidence. This we might have already studied in electromagnetic wave. So in case of oblique incidence, what are the different types of polarizations we have? Okay, so the different types of polarizations is what we study. Okay, so polarization concept, what is polarization and what are the different types of polarizations we will be studying. Okay, and based on this polarization concept, so we will be classifying the electromagnetic waves or the into three different types or three different modes. Okay, so TE mode, TM mode, and TE. So transverse electric mode, transverse magnetic mode, and transverse electromagnetic mode. So what is this TE wave, what is this TM wave, and what is this TEM wave, we'll be discussing. Okay, and in each case, so in case of TE wave, for example, so I will be deriving the first thing we will be deriving the field expressions. So what are the field components that are there, and what are their expressions we will derive. Okay, and then we will be discussing certain characteristics of the wave mode, right? Characteristics of the mode, like what is the minimum cutoff frequency, what is the launching angle, what is the cutoff wavelength. Okay, and then what is the velocity of propagation for this TE mode. Okay, what about the attenuation in case of the wave, the TE mode, what is the wave impedance in case of TE mode, all these things. Similarly, for TM mode also we will do the same thing for TEM mode also. So in each case, we will first derive the expressions for field components. Okay, so what field components exist? Okay, for example, here what I mean is, so electric field if I take, okay, this electric field is generally, if I consider an unbounded electric field, it will exist in along x-axis, along y-axis, and along z-axis, isn't it? So there will be a component along x, there will be a component along y, and there will be a component along z. So Ex, Ey, and Ez, all of them exist. Okay, but when you incident this electromagnetic wave in the boundary inside the waveguide, so what happens? Which components exist? Which components will survive? Which components will get zero, okay, or get diminished? So similarly, what about the magnetic field? So what are the field components that exist inside the waveguide? Okay, and what are their expressions? Okay, we will derive from that, and we will be deriving one very important concept. So the design of the waveguide. So what is the minimum spacing that I require for the wave for the waveguide to be placed? So all these things we will be discussing in the first unit. Okay, so the first unit is basically the related to the electromagnetic wave propagation in a bounded medium. Okay, so in the EM theory, we have studied the general propagation of EM waves in an unbounded media. Okay, so there are no boundary conditions at all. Now we are applying the boundary conditions and we are seeing how the waveguide will behave, or how the wave inside that bounded structure will behave. What are the components that will survive? Okay, what are the characteristics, okay, of this, and how, based on what the type of polarization, how we get different types of modes. Okay, what are the characteristics of these modes? Everything we will be discussing in the first unit. Okay, then coming to the second unit. So second unit has two parts. Okay, so we have two parts in the second unit. So first part, okay, unit 2, part 1. So this, right, as I said, in the first unit we have studied about uh, right the guided waves using a general structure or a theoretical assumption of parallel plane waveguides. So whereas in unit 2, what we will be doing is we will be considering practical structures that are used for transmitting right the wave, the electromagnetic signals or microwave signals. So which are the rectangular and circular waveguides. Okay, so rectangular and circular waveguides are the practical structures, practical waveguides, waveguiding structures or practical transmission lines that are useful or that are used to transmit the microwave or EM wave signals. Okay, so in the first unit we have studied about the general case. Okay, using a theoretical assumption of parallel plane waveguide. Now what we do is we will be studying with the help of practically useful or practically used structures, which are called as the right rectangular and circular waveguides. Okay, so here also again we will be studying the same case for both rectangular and waveguides and circular waveguides. So firstly we will be discussing the general structure, how the waveguide is constructed. Okay, and then we will be studying or we will be deriving the expressions for field components. So inside this right okay, inside the waveguides, so what are the fields that exist, okay, what components of the fields exist and what are their values, we will derive that. Okay, and then we will be discussing about the characteristics of the right different modes that exist in case of right waveguide modes that exist in case of rectangular and circular waveguides. Okay, so TE mode, again the same thing, concept of what is TE mode, what is TM mode, what is TEM mode, and how the different modes have their properties, etc., etc. And again here also we will be deriving certain expressions for attenuation, wave impedance, okay, wave impedance, etc. Right? So the parameters of the EM wave inside these modes, we will be discussing them and we'll be doing some problems. Okay, so this is the first part. Okay, so it is just a continuation, it is just a logical continuation from the first unit. Okay, in the first unit you have introduced the concept of boundaries with the help of a general structure. Here, okay, a theoretical structure. Here we will be discussing the practical versions of the waveguides, rectangular and circular. Okay, next coming to the part 2. So the part 2 discusses about something very important one, which is called as cavity resonators. So we know what is the resonating circuits, right? So here we will be discussing about the microwave resonators. So what is a cavity resonator? So firstly, what is the principle of resonance? So we will introduce that. What is the principle of resonance? What is the importance of Q value for a waveguide? Okay, and Q value for a resonator. Okay, and then we will be discussing the general structure of a cavity resonator and how it will resonate, okay, at a particular frequency, etc. Okay, so the second part is completely discussing about the cavity resonator concept. Okay, so what is meant by resonance, what is meant by Q value, what is its importance in case of waveguide, in case of resonators. Okay, and then we will be discussing a special structure called as cavity resonator. Okay, so two cavity resonator is a very important device that we use, okay, in general. So this is the second part of the second unit. So where we will be discussing about the cavity resonators. Next, coming to the unit 3, right? So the third unit of our syllabus is about microwave circuits and components. Okay. So whenever I want to construct, okay, whenever I construct a closed connection of the various components that are there, okay. So generally, we have a source, we have some transmission line, and then we have a receiver. Okay, so you have a complete system or a circuit, right? So whenever there is a connect, whenever we have a microwave circuit, a closed loop of interconnection, then how does the power flow happen, or how does the voltage or current will happen? Can we approximate microwave components or microwave devices with the circuit theory? Okay, so generally we say that transmission line theory is a field theory. Okay, so it is a distributed line. Can we do the analysis of microwaves with the help of circuit theory, right? So that is what the question we ask, right? Okay, and the answer is yes. Yes, we can approximate, or we can analyze microwave circuits or microwave whatever the structure system we have, and using circuit theory also, and especially using the concept of two-port networks. So using the concept of two-port or multi-port networks, we can analyze or we can understand the behavior of microwave components and microwave circuits. So that is what we do in the third unit. Okay, we understand the behavior or working or the characteristics of various microwave components that can be used to construct larger circuits. Okay, circuits comprising of a generator or transmitters, right? Various okay, other functionalities like amplifiers, etc., etc., to the load. Okay, so a closed loop system. You can also construct a closed loop system, and the understanding or the behavior of this closed loop system can be done with the help of circuit theory concepts. Okay, so here we will be studying first understanding what is a microwave circuit. What do we mean by a microwave circuit, right? And what is the concept of normalized current and normalized voltage? So what do we mean by normalized current, normalized voltage, how it is different from the general terms that we will discuss? Okay, and then we, as I told you, we can approximate or we can understand or characterize the behavior of microwave components with the help of circuit theory. Okay, by using the concepts of two-port networks or multi-port networks. Okay, so here for doing that we introduce a concept called as, or a special kind of parameters called as S parameters, scattering parameters. Okay, similar to that of Z, Y, ABCD, H parameters. So all these at low frequencies, but at high frequencies these concepts do not work. Okay, so at high frequencies we need some kind of parameters that can be useful for us for conveying the information or conveying the characteristics of the right components that we are using. Okay, so that is exactly done by these S parameters. So we will be studying what are called as S parameters, scattering parameters. Okay, right? What is a scattering parameter, why we use them, why can't we use the other parameters? Okay, and what is the general definition of these S parameters, right, etc., etc., we will deal here. Okay, and right, we will establish all the mathematical, right, things that are required, and then after this we will be studying the characteristics of the different microwave components. Okay, so for example we have right, microwave junctions. Okay, we will be studying about microwave junctions. So junction devices that are useful for making connections or junctions. So like T junction, H plane T is there. We will be studying what is a H plane T, and where it is used, what is the property of it, and then we'll be studying what is a E plane T, and then we'll be studying what is a magic T, and then what is a rat race T junction, all these things. So these are the T junctions. Okay, so these are the junctions or components that are used for forming a junction. Okay, microwave junctions. Okay, that is splitting of power or connecting of power. Okay, so right, we will be studying about all these different microwave junction devices like H plane T, E plane T, magic T, rat race junction. So what is this, what is a junction, what are their behavior, where it is used? Okay, and what are the S parameter matrix of these things? So we'll be calculating the S parameter matrix of for all these things, and then from there we'll be understanding the behavior of them. Okay, then we will be studying, after this we'll be studying something called as directional coupler, which is also again used for connecting various microwave devices, a very important device called as directional coupler. And then after that we will be studying something called as ferrite devices, microwave ferrite devices, okay, so which are very useful in forming the microwave circuits. Okay, so we will be studying something called as isolators, okay, circulators, phase shifters, right? So all these are ferrite devices made up of ferrite components, magnetic components. So these ferrite materials are very much useful in forming special kind of devices, okay, which are helpful in forming the microwave circuits. For example, I have an isolator. So as the name indicates, so isolator means it is isolating something or separating something. What it separates? It separates the source from the rest of the circuit. Okay, so you have an isolator, right, which will pass only the signal in one direction. Okay, so it will block the signal in other directions. Okay, yeah, so that is right. Similarly, we have circulator, we have phase shift, okay, phase shifter, etc. So all these are the different kind of ferrite devices. So in the third unit, we will be studying about the various components that are required or useful for forming the microwave circuits. Okay, so here, right, we will be discussing about circuit theory, right, and using the S parameters, we will be understanding the behavior of the various components that we have. Okay, right. Next, coming to the fourth unit. So the unit 4 of our syllabus discusses about the, right, again there are two parts in it, so every unit has two parts. So here the part 1, the first part of this right, fourth unit, so this discusses about the microwave tubes. Okay, so tubes are the structures that are useful for generating the microwave signals. Okay, so right, the first part discusses about the tubes. So what is, right, firstly we will discuss what are the limitations of the conventional tubes. Okay, conventional tubes like okay, various generators we have. So what are the limitations of them, why can't we use them at high frequencies, and then we will be discussing one very important concept called as bunching. So what is meant by bunching, or what is meant by voltage modulation, velocity modulation. Okay, so what is bunching, what is velocity modulation, how do we under apply this, right, using the mathematical applications, mathematical analysis we will do for the, right, all this bunching concept and velocity modulation. So and then we will see how this can be applied in the tubes, okay, in forming the microwave tubes. Okay, so in our syllabus, we will be discussing about two very important microwave tubes. So one is, right, okay, two cavity. Sorry. uh, so right, one is the right, a twin tube, right, a two port or a multi port, right, a microwave tube. Okay, so general structure, and the other is reflex transfer. Okay, so these are the two very important tubes that we have. Okay, so we will be studying about them, right. Firstly, we will be studying what is, right, a twin structure tube. Okay, and then we will be studying about the reflex transfer. Okay, so here it is all about tubes. What is a microwave tube? What are the limitations of the conventional tubes? Okay, right? And then what is the concept? The main concept is bunching. So what does mean by bunching or velocity modulation? Or right, how it is useful in forming the tubes we will study. Whereas coming to the second part of the fourth unit, so it is also related to this. So here we will be studying about some special devices called as magnetron, right. So these are different, right, type of amplifiers. It's basically right, microwave amplifiers. So a microwave or amplifier and an oscillator, so a generator and oscillator, right. Okay, so we will be discussing some special microwave amplifiers here. Okay, so one is a magnetron, other is a TWT, and the other is a BWO. Okay, traveling wave tube, right, and okay, bunching oscillator. So these three devices, these three special feedback or microwave amplifiers we will be discussing in the second part of the fourth unit. Okay, so this fourth unit is entirely about the devices which will generate the microwaves or signals or the signals of high frequencies. Okay, and also the oscillators or amplifiers at the microwave frequencies. Okay, so we will be discussing the different oscillators and amplifiers in this part. Okay, and then the last unit, which is the the final unit of our syllabus. So again, it has two parts. So the first part of the fifth unit discusses about solid state devices. Okay, so this is unit 5. Okay, so in the first part we will be discussing about the solid state devices. As solid state devices means active devices or devices which perform non-linear operations, okay, like diodes and transistors. So at microwave frequencies, our normal PN junction diode or BJTs won't work. Okay, so we need devices at that to work, to amplify or to rectify or to perform the diode or transistor action at that particular frequency, isn't it? So that is why here we construct special kind of structures that will perform the amplification or rectification or whatever the operation of diode and transistor at high frequencies. Okay, so here in our syllabus we will be limiting to only two terminal devices, that is diodes. Okay, so we will be studying about the special characteristics of 3 or 4 diodes. Okay, one is varactor diode, okay, then pin diode, okay, pin diode, then gun diode, okay, and then next is impact diode. Okay, so for these 4 diodes, for each, all of them are diodes, different diodes at microwave frequencies. So for each diode we will be discussing their construction. Okay, what is how we construct them, what is the principle of operation, what are the characteristics means VI characteristics of these diodes, okay, and where they are useful applications. Okay, so 4 important diodes: varactor diode, pin diode, gun diode, and impact diode. In each case, we will be discussing their characteristics, we will be discussing their construction, we will be discussing their principle of operation and applications. Okay, so that is the first part, which is about the solid state devices at microwave frequencies. In the second part, we will be discussing a very small and useful concept called as strip lines. Okay, so nowadays we are using these strip lines very effectively in mobiles, in satellites, etc. The small antennas or transmission lines. Strip lines means it is a very micro sized transmission line. Okay, a transmission line of very small size or small radius or diameter is called as a strip line. So especially useful in case of mobiles, etc. So we will be discussing that in detail. So in the last part, in the second part of the unit 5, so we'll discuss what is a microwave strip line, okay, what is a fin strip line. Okay, so these two topics, so what is a strip line, what is a micro strip line, and what is a fin strip line, we will discuss in the unit 5, the second part. Okay, so this is the brief overview of the syllabus that we are going to discuss in this course. Okay, so we will be starting taking from the EM theory, we'll be continuing from the EM theory. So as we discussed in EM theory, we will be discussing about the unbounded transmission. Now we will be applying the boundary conditions. Okay, right, and in case of boundary conditions, how the EM wave will behave or vary. Okay, and we will be discussing with respect to that particular spectrum, right? So that is 1 gigahertz to 1000 gigahertz, right? So in that spectrum, how does that spectrum signal will vary? Okay, so we will not be discussing about the general EM wave, we will be taking that part of that, right, and we call that as a microwave. Okay, right, and how this microwave signal will behave inside the bounded media. Okay, so that we will start, and then we will be discussing about rectangular waveguides, circular waveguides, and then we will be discussing about cavity resonators. Okay, in the first 2 units, and in the third unit we'll be discussing something related to microwave circuits. What is the circuit theory in microwaves? What about the components that we use? Different components like circulator, isolator, plane junctions, directional coupler, etc., etc. Their characteristics and everything in the third unit. In the fourth unit, we'll be discussing about the generation and amplification of microwave signals. Right? We discuss about something about reflex klystron, traveling wave tube, magnetron oscillators, the tubes and oscillators that we use. And in the last part, we will be discussing about solid state microwave devices and the strip line. Okay. So this is the brief overview, right? From right next onwards, we will be discussing the first unit. In the next lecture, I will be discussing the first unit. Okay, right, and we'll continue this. Okay, and one very important, the last point that we have to understand is microwave signal is nothing new. It is just an EM wave signal having a frequency of 1 gigahertz to 1000 gigahertz. So whatever we studied in EM theory, we will just carry forward. It is nothing new. Okay, so a microwave signal is just an electromagnetic wave signal. This point we have to be very clear. Okay, only thing is it is of high frequency. It is of a particular frequency which is 1 gigahertz to 1000 gigahertz, which is very high. So therefore, to handle it, we require structures that are right, that can handle high power and less losses. So that's, those structures are called as waveguides. That is why we are studying all the waveguides. Okay, so yeah, so this is about it. So right, let us stop the lecture for today. In the next class, we will be starting the first unit.